Hello, welcome back to MEC 416/816 Engineering Acoustics. In this video, we are going to combine the three equations that we saw in the previous video and then use them to find a single differential equation with a single dependent variable, which will be the linear acoustic wave equation. We're going to start by taking the divergence of equation 13. That is where we take del dot that equation, and so we'll get del on the left-hand side dot the quantity rho 0 times partial u over partial t, and that then becomes equal to minus del squared p, and we just note here that del dotted with itself is a scalar quantity, which we call del squared. Again, if you're not familiar with the del operator, you should just take a moment and look that up. From there, we are now going to take the time derivative of equation 12. I'll just briefly scroll up. You can see what it looks like there at the top of the screen. We're going to take the time derivative of that, and we're going to end up with rho 0 times partial squared s over partial t squared plus del dot the quantity rho 0, and so rho 0 here is not dependent on time, times partial u over partial t. And so both the taking a time derivative and the del dot operator are linear operators, so we can exchange their orders. So I brought in that time derivative inside that second term, inside the parentheses. We're then going to take equation 16 and subtract 14 from it. This will give us that rho 0 times partial squared s over partial t squared is equal to del squared p. And then from equation 7, we're going to recall that the pressure is equal to the bulk modulus B times the condensation. And then if we divide by the bulk modulus, we'll find that the condensation is equal to the pressure. And so what we'll find here is that rho 0 divided by our bulk modulus B, let me just rewrite that a little bit, times partial squared P over partial T squared is equal to del squared P. And from here, we get that the quantity 1 over c squared P sub tt, that's now our second derivative there. And actually, we're going to write it as partial still. Partial P over partial T, that should be partial squared T squared is equal to del squared P. And that is our linear acoustic wave equation. And C here is the thermodynamic speed of sound. So again, this is the linear acoustic wave equation, which we can abbreviate as the law. Okay, so for an ideal gas, the speed of sound can also be defined as c squared is equal to gamma times p0, that's our atmospheric pressure, divided by rho 0, where gamma is the ratio of specific heats. Ratio of specific heats, and you can find that in Appendix A10. And another expression here is that c squared is equal to gamma times r times the temperature T in Kelvin. where R is the specific gas constant again, and TK is the temperature in Kelvin. And then finally, the speed of sound is also proportional to the square root of the absolute temperature. And so in terms of a speed C0 at 0 degrees Celsius, this becomes that the speed of sound C is equal to that C0 times the square root of 1 plus T in Celsius divided by 273, where again T is the temperature in Celsius. Okay, that concludes this video and the series of lectures on deriving the linear acoustic wave equation. In the next week, you will then start to watch videos on the velocity potential, as well as plane sound waves, and then also standing waves as well.